I'm Travers, and I'm currently an undergraduate at Newcastle University. For the past 6 months, I've been undertaking research in the Microsystems Research Group. This research looked into how best to manage concurrently running programs on the Linux operating system. It has been shown that Linux governors do not do the best job at managing concurrently running programs, and so a runtime script was produced, and today I'll be demonstrating this script I've made and how it works. Firstly, the main aim of this project is to get the best performance per watt of power for the system as a whole when running multiple programs. This is achieved by maximising the instructions per second per watt for the system. The amount of energy used also closely follows the maximum IPS per watt, so we should see reductions in energy as well. The program works by taking performance counter results of external programs inputted into the script, and then using models created through linear regression, it maximises the IPS per watt. When more programs are added to the script, they are also taken into account to decide how best to allocate resources. The resources that can be allocated with this script are the frequency and core allocations to each program. Today I'll be showing you how this program works on the Intel Core i7 processor. Hyperthreading has been disabled. As you can see down here, there's only 4 cores available, and it will be running on Ubuntu 12.02.4. The programs I'll be using for the script are from the Parsec benchmark suite, and I'll be using Keneal and FreckMine to demonstrate how this script works. Before we get into the project and see how the script works, it should be noted that Keneal is a very memory intensive program with a lot of memory requests, and FreckMine on the other hand is very CPU intensive. This should give a good indication on how cores and frequency are allocated. So the first test we're going to do is a control to see how Linux handles these 2 programs when running the on-demand governor. It can be seen here that if we run this, the on-demand governor here is actually running at the moment. We've got a couple of other scripts up here. These ones are to plot the results once we actually run the program. This is to get performance counter results for the system, and run2 is actually another script, and this is simply just runs Keneal and FreckMine in parallel. So let's run the program and see what happens. So we've currently set the 2 programs off running. They should be able to see down here we've got FreckMine and Keneal running. We will now start to plot the results. Okay, so here we have frequency. As you can see, the on-demand governor does what it's supposed to do. When utilization goes over threshold, it goes up to maximum frequency. This is 3.6 gigahertz, or sorry, 3.7, as can be seen here. This is how the IPS per second of the system, and as you can see, all the cores are mixed up at the moment. Programs may be switching between cores, and the highest we're getting at the moment is about 1.4 to the 9 instructions per second. If we let this run for a little while, we'll be able to see that it stays at around this level. It should be noted that the average is down at about 8 times 10 to the 8 instructions per second. We won't be looking through the whole program today, so I will quickly give that a stop. Okay, both programs will be ended now. We'll quit the live plotting. Okay. Next we're going to see how the program works when we're inputting into the script and the script's managing. So now we'll be looking at how the runtime script manages these programs running concurrently. So we have the 2 input scripts for the programs. This simply feeds information into the actual runtime script, and this is, say, thread information, the thread numbers, and the PIDs of these threads. So we'll set this off running and see what happens. So if we give this a run, We will now enter in MEng. MEng should now be running down here, as we can see, and we'll now add into it Keneal. So if we both have them both running now, if we expand this a little bit, we can see that that one program has an infinity list of 0 to 2 and 1 is 3. If we now open up our GNU plot, we should see how this is organized. So here we can see the programs have actually been split between separate cores. We have Keneal running down here at quite a low IPS, and we have MEng able to increase its IPS up to quite a high value. We'll let that run for a little bit. We can also see up here we have the frequency. This is now being trying to assign to different cores different frequencies. Again, we have Keneal on one core down here, and we have MEng up on 3 cores up here. This is the way the runtime script, has decided to allocate the resources, and we'll see what happens. It can also be seen down here that MEng is using 270% of the CPUs, while for Keneal it's limited to just 100. Should be noted that Keneal at some point may need a higher frequency throughout the program. This is maybe because the way the program works changes over the runtime of the program. Can now be seen. But no programs are now running. And we go back down to minimum frequency, and it can be seen in the script here, it says no program running. So hopefully today it's been demonstrated how this runtime script I produced works, and how it assigns different frequencies and different core allocations to different programs inputted. We've seen energy reductions of up to 23% when running concurrent programs together for the system as a whole. This is a really good energy savings, and hopefully this research can be taken further. I would like to thank Richard, Faye and Alex of the Microsystems Research Group for giving me a lot of time and help throughout this research.